Scientists just found out that the Earth's crust beneath the Marmara Sea is sending seismic signals that look exactly like the kind that show up before a major earthquake. An earthquake that can shake entire coastlines and send waves racing toward crowded cities. For years, scientists focused on visible ruptures on land because they could measure and map them easily. But now, they made a detailed map of a huge fault system under the seafloor. The Mediterranean already sits at a dangerous crossroads where massive tectonic plates meet. Those plates push, scrape, and stretch against each other, and that constant motion creates massive stress. The crust there grows thinner over time, and thinner crust means it can't absorb stress easily. Stress builds, pressure mounts, and the signals coming from below show that parts of this fault system have started to move in unusual ways. The new map shows that future large earthquakes may begin at the boundaries where weaker and stronger sections of the crust meet, or along edges of highly resistive zones. They even pinpointed one of the most likely locations beneath the Marmara Sea. What makes this discovery so intense is the scale. The faults in the seabed form long corridors where energy can accumulate for decades or centuries. Scientists warned that this setup is the kind that can produce a super earthquake, a massive seismic event capable of shaking large coastal cities and possibly generating tsunamis. A tsunami forms when the seafloor shifts vertically and displaces huge amounts of water. So, it looks really plausible in this setting. The water it sets free radiates outward in powerful waves that can cross entire seas. The Mediterranean holds dozens of densely populated shorelines, so it could affect millions of lives. Speaking of that, let's zoom in on Istanbul, Turkey's largest and most populous city. The massive fault line sitting right under it doesn't act the way scientists thought it did. For years, experts looked at the main Marmara Fault, a branch of the North Anatolian Fault running beneath the Sea of Marmara, and worried it might rip in one single monstrous rupture. That kind of break could unleash a megaquake in the high sevens or beyond. But when scientists ran detailed computer simulations covering more than 10,000 years of earthquake cycles, they saw something different. The fault doesn't behave like one giant zipper waiting to unzip all at once. It behaves more like a row of connected tiles that break in sections. And the reason comes down to what's happening miles below the seafloor. It's called rheology. Simply put, how materials deform under stress, how rocks bend, stretch, or snap when you squeeze them hard enough. Under the central Sea of Marmara, giant piles of compacted mud, sand, and debris sit on top of warmer crust. In those upper layers, the sediment usually deforms slowly and steadily, especially at shallow depths where pressure and heat interact in specific ways. Deeper down, higher temperatures weaken the rocks. Warm rock flows more easily than cold rock. That heat acts like a built-in brake system that limits how far a rupture can tear through the crust. When researchers built a 3D earthquake cycle model, they fed in real heat flow measurements, rock friction data, and structural details, and replayed thousands of years of seismic activity. When they included both sediment thickness and temperature differences, the model finally matched history, including the powerful quakes of 1766 and 1912. And none of the simulated events exceeded magnitude 7.3. That level of shaking can collapse buildings, fracture infrastructure, and cause landslides. But it differs from the nightmare scenario of one continuous coast-to-coast rupture. Instead, different sections behave in different ways. The western segments produce more regular earthquakes, including magnitude 7.2 events roughly every 150 years. The eastern sections generate smaller double quakes, back-to-back events between magnitude 6.2 and 6.8 about every century, and a magnitude 7.0 roughly every 500 years. Parts of the fault don't snap at all, but creep. Scientists call it shallow creep, which just means the fault slowly slides without producing a major quake. It releases tension quietly, like letting air out of a balloon instead of popping it. GPS measurements and clusters of repeating small quakes over the past 20 years confirm that slow slip near the central basin. So, what does this mean for Istanbul, a city of over 15 million people sitting practically on top of this system? A magnitude 7 or 7.3 quake close to the city could still rock neighborhoods, especially if two strong events strike in quick succession. Infrastructure, older buildings, and densely packed districts are at the highest risk. The fault hasn't produced a major rupture in this section since 1894, which means there's more than 130 years of accumulated strain. The simulations show major events could strike in the coming decades. Then there's Santorini, where more than 28,000 earthquakes happened in just a few months in early 2025. Most of the quakes stayed small, but some reached magnitude 5, strong enough to fracture walls, rattle nerves, and push authorities to close schools and evacuate parts of the island. And this wasn't just tectonic plates grinding like they usually do. This swarm moved. The epicenter shifted gradually northeast toward the Colombo submarine volcano about 5 kilometers offshore. That migration told scientists magma was on the move. Researchers calculated that roughly 80 billion gallons of it, enough to fill about 120,000 Olympic swimming pools, surged upward from depths around 11 miles beneath the surface. It climbed fast, then stalled about 2 to 2.12 miles below the seafloor. And all this was going on along the Hellenic Arc, one of Europe's most active subduction zones, where the African plate dives beneath the Eurasian region. Earthquakes often migrate across that span toward nearby islands. History backs that up. The 1956 Amorgos earthquakes unleashed massive shaking and a tsunami across the region. So when 28,000 tremors light up the seismic network, you pay attention. This episode changed how scientists understand volcanic swarms. Now they know magma can intrude, fracture miles of crust, reshape underground reservoirs, and still never surface. It can load the system for the future without pulling the trigger today. And that matters because when magma moves like this, it changes stress fields underground and how future quakes might breed. The good news is that scientists now have really cool monitoring tools that feed real-time seismic feeds, underwater pressure sensors, and repeated gas measurements near volcanic vents into integrated hazard models. If magma starts accelerating upward again, researchers will see it and will take action. And there's another bold new idea in earthquake and tsunami warning: using undersea internet cables for this purpose. Nearly 1 million miles of those fiber optic lines on the seabed were designed to carry data. But scientists discovered that they can also detect tiny changes in light signals caused by seismic vibrations. In simple terms, when the ground shakes, the cable feels it. And this could be incredibly useful because forecasting earthquakes, even on land, is tricky. In the ocean, it has felt almost impossible as you can't scatter thousands of sensors across the seafloor easily. But those cables already sit there, stretching across deep trenches and continental shelves. If researchers use them as sensors, they can monitor tectonic movement in real time across huge areas. For a region like the Mediterranean with hidden faults, active volcanoes, and crowded coasts, that system could offer precious seconds or minutes of warning. Seconds sound small, but early alerts let trains stop, gas lines shut down, and people move away from immediate danger. The fiber optic cable used for Seafloor Project, or FOCUS in the short version, didn't warn anyone about real disasters yet, but it had 2 false alarms. It reacted to a submarine landslide and weight bags that pushed the cables down. It proves the system works and could be life-saving in case of real danger, especially in vulnerable regions such as the Mediterranean. It shaped civilizations for thousands of years, and now science reveals it still shapes itself. They can't stop tectonic plates or cool magma chambers, but they can understand patterns, reduce vulnerability, and design cities smarter. That's it for today. So hey, if you satisfied your curiosity, then give the video a like and share it with your friends.